The XHand system is a real-time expressive hand avatar that enables realistic and interactive hand animation. It uses a combination of machine learning and computer vision techniques to generate realistic hand motion and finger articulation. The system consists of three main components: hand pose estimation, finger articulation modeling, and hand animation rendering. The hand pose estimation module uses a convolutional neural network, CNN, to predict the 3D hand pose from a single RGB image. The CNN architecture is based on the U-net structure, with an encoder-decoder design that allows for efficient feature extraction and pose estimation. A novel loss function combining mean squared error, MSE, and cosine similarity is proposed to improve the accuracy of the pose estimation. The finger articulation modeling module uses a probabilistic approach to model the finger joint angles and fingertip positions. A Gaussian mixture model, GMM, is proposed to represent the distribution of finger joint angles and fingertip positions, and the expectation maximization algorithm is used to learn the model parameters. The GMM is conditioned on the hand pose and finger type, allowing for realistic finger articulation and motion. The hand animation rendering module uses a physics-based approach to simulate the hand motion and finger articulation. The Open Dynamics Engine, ODE, is used to simulate the hand motion and finger articulation, and the hand animation is rendered using the OpenGL API. The system also includes a user interface that allows users to interact with the hand avatar in real time. The XHand system is evaluated using various metrics, including mean squared error, MSE, and structural similarity index, SSIM. The results show that the XHand system achieves state-of-the-art performance in hand pose estimation and finger articulation modeling, and demonstrates realistic and interactive hand animation. The XHand system has a wide range of applications, including virtual reality, augmented reality, and human-computer interaction. Limitations of the system include the requirement for a high-quality RGB image and the need for further improvement in finger articulation modeling. Future work includes exploring the use of other machine learning techniques, such as recurrent neural networks, RNNs, and generative adversarial networks, GANs, to improve the accuracy and realism of the hand animation. XHand is a rigged hand avatar that captures the geometry, appearance, and poses of the hand, created from multi-view videos and utilizing mono-pose parameters to generate high-detail meshes and renderings. This approach enables the generation of photorealistic hand images in real time for a given pose sequence. To enhance the efficiency of geometric information extraction from images, the authors incorporate a part-aware Laplace smoothing term, applying various levels of regularization. A mesh-based neural renderer is employed to achieve photorealistic hand rendering, leveraging latent codes from feature embedding modules while maintaining topological consistency. This method preserves detailed features and minimizes artifacts through various regularization levels. The authors evaluate their approach using the InterHand2.6M dataset and the DeepHandMesh collection, demonstrating that XHand outperforms previous methods, providing high-fidelity meshes and real-time rendering of hands in various poses. The key contributions of this paper include a real-time expressive hand avatar with high-fidelity results on both rendering and geometry, an effective feature embedding module to simplify training objectives and enhance prediction accuracy, and an end-to-end framework to create photorealistic and fine-grained hand avatars. The proposed method outperforms previous approaches, as indicated by the promising results. The author's approach has significant implications for applications requiring realistic hand modeling and rendering, such as computer-aided design, virtual reality, and human-computer interaction. The paper addresses the challenges in capturing geometric details of hand models using current methods, such as Moon et al.'s encoder-decoder framework and Gan et al.'s optimized pipeline. These approaches have limitations, including difficulty in rendering photorealistic hand images and overlooking variations due to joint movements. The authors propose their XHand approach, aiming to simultaneously synthesize detailed geometry and photorealistic images for drivable hands. Their method involves feature embedding modules designed to obtain linear blending skinning, LBS, weights, vertex displacements, and albedo by combining the average features of the mesh with pose-driven feature mapping. The paper also discusses various alternatives available for neural hand representations, such as hand avatar, hand RF, LISA, and live hand, which focus on signed distance functions, SDFs, volumetric rendering, and neural implicit models with hand textures. However, these methods have difficulty capturing the details of hand mesh geometry. The author's proposed method uses the parametric hand model mono to initialize the hand geometry and maps the pose parameter theta and shape parameter beta onto a template mesh. They introduce a personalized vertex displacement field to allow for extra deformation for each vertex in the template mesh, resulting in a refined posed hand mesh M-fine. The paper concludes by discussing the subdivision strategy used to enhance the mesh resolution and capture intricate features. The XHand framework is a novel approach to generating detailed geometric hand meshes and achieving photorealistic renderings in real time. This framework utilizes 3 feature embedding modules to obtain the displacement field, linear blending skinning, LBS, weights, and albedo. These features are applied to a subdivided mono template, which is obtained through a subdivision function that extracts the high-resolution template mesh and LBS weights. The feature embedding modules, denoted as Psi-D and Psi-LBS, are designed to capture intricate details of hand mesh and LBS weights. The displacement embedding Psi-D generates vertex displacements, while the LBS embedding Psi-LBS derives LBS weights. These modules rely on average features of hand mesh and compute offsets of features in different poses. The mesh features are predicted using these modules, given hand pose parameters. The refined mesh at time t is formulated as a function of the subdivided mono template, vertex displacements, LBS weights, and hand pose parameters. The feature embedding module extracts mesh features using a personalized hand mesh and its pose, and represents mesh features using a designed embedding function. This function combines the average vertex features of hand mesh with a pose decoder that projects the pose and latent code onto the implicit space. The feature space is aligned using a kernel function. The XHand framework enables accurate representation of hand geometry and realistic rendering in real time. The subdivision function is defined in equation 3, while equations 4 and 5 formulate the prediction of mesh features and refined mesh. The feature embedding module is defined in equation 6, and the embedding function is represented in equation 7. The framework's effectiveness is demonstrated through comparisons of mesh refinement and texture between the original and subdivided mono templates, as shown in figures 2 and 3. The XHand framework has the potential to revolutionize the field of computer vision and graphics, enabling realistic and detailed hand modeling and rendering in real time. The proposed feature embedding module is designed to predict personalized mesh features, including LBS weights, displacements, and albedo, based on the input pose. This module consists of 3 different feature embedding modules, Psi-LBS, Psi-D, and PSR, which utilize a pose decoder, latent code, and mapping matrix to generate the desired features. The personalized mesh features are derived by combining the average vertex features with the pose-dependent offsets. The LBS weights dubent are obtained by combining the average LBS weights FLBS with the pose-dependent offsets, which are generated by the pose decoder Phi-LBS, latent code QLBs, and mapping matrix KLBs. Similarly, the vertex displacements dt are obtained by combining the average displacements FD with the pose-dependent offsets, which are generated by the pose decoder Phi-D, latent code QD, and mapping matrix KD. The feature embedding modules allow for the interpretable acquisition of hand features corresponding to the pose theta t. The average mesh features are stored in FM, while the features' offsets are affected by the pose theta. The training objectives are simplified by taking into account the average features constraints, leading to faster convergence and improved accuracy. The mesh rendering process involves inverse rendering and mesh-based neural rendering. Inverse rendering synthesizes hand images using the Lambertian reflectance model, which assumes that the skin color follows a Lambertian reflectance model. The rendered image B can be calculated from the spherical harmonics coefficients G, the vertex normal n, and the vertex albedo ρ. The pose-dependent albedo ρ can be obtained from the feature embedding module PSR with average vertex albedo f ρ, pose decoder φ, latent code Q-row, and mapping matrix K-row. The mesh-based neural rendering method takes advantage of the consistent topology of the refined mesh, allowing for efficient and high-quality rendering. The mesh is explicitly represented by triangular facets, and the features that describe meshes, such as position, color, and normal, are associated with their respective vertices. The attributes of intersection points can be calculated by interpolating the three vertices of the triangular facet to its intersection point. The efficient differentiable rasterization ensures the feasibility of inverse rendering and mesh-based neural rendering. Given a camera view pi, the mesh-based neural render C, pi, synthesizes the image with respect to the position x, normal n, feature vector hand ray direction d, where x, hand n are obtained through interpolating with mfine. The neural render C, pi, contains the latent codes qd and qrow detached from psi-d and psr, and feature vector keyrender. The XHand model is a neural hand representation that leverages a neural renderer to generate personalized hand representations from multi-view image sequences. The neural renderer consists of 8 fully connected layers with ReLU activations and 256 channels per layer, excluding the output layer, and features a skip connection that concatenates the input to the 5th layer. The training process involves 3 steps: initialization, training feature embedding modules, and training the mesh-based neural render. Initialization is crucial, as random initialization can lead to estimation errors in the feature embedding modules. To address this, the reconstruction result of the first frame is treated as the initial model, and the vertex displacement D and vertex albedo rho of the hand mesh are jointly optimized through inverse rendering. The loss function during initialization is formulated as the sum of the L1 loss between the rendered image and the ground truth image, and the Laplacian terms L times D and L times rho, which regularize the mesh optimization. The outcomes D and rho are used to initialize the feature embedding modules psi-d and psr, while the initialization of psi-lbs is directly derived from the mono model. The loss functions of the feature embedding modules involve inverse rendering to learn the parameters of the modules. The rendering loss LRGB is combined with a regularization term LREG, which includes the part-aware Laplace smoothing term LP-lap to reduce excessive roughness in albedo and displacement. The LP-lap term is defined using hierarchical weights phi-plap to balance the weights of regularization via different levels of smoothness. The regularization terms LREG also include LMask, L, and LD, which ensure that the optimized hand mesh remains close to the mono model. LMask is the L1 loss between the mask rendered during inverse rendering and the original mono mask, while L penalizes the edge length changes of the mesh edges, and LD constrains the degree of displacement. Once the latent codes QD and QRow of the feature embedding modules are detached, the loss function LNU is used to train the neural renderer C. The neural renderer C is trained to generate personalized hand representations from the latent codes, and the loss function LNU is designed to minimize the errors between the generated images and the ground truth images. The use of hierarchical weights in the part-aware Laplace smoothing term LP-lap allows for better constraint of feature optimization in different scenarios. The threshold P can be dynamically controlled through the quantiles of the Laplace matrix A, allowing for more flexible regularization. The authors present their experimental setup and results for the proposed XHand model, a neural rendering approach for hand mesh reconstruction. Utilizing 2 datasets, InterHand2.6M and DeepHandMesh, the experiments primarily employ the 5 fps version of InterHand2.6M, with the XHand model trained on 20 views across 50 frames for each sequence. PyTorch and the Atom optimizer with a learning rate of 5e4 are employed, along with the off-the-shelf renderer NV-Diffrast for differentiable rasterization. Positional encoding is performed on the input data before feeding it into the rendering network. The feature embedding modules are first trained for 500 epochs using inverse rendering, followed by joint training with the neural render for 500 epochs. Evaluation metrics include peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, and learned perceptual image patch similarity, LPIPS, as well as the average point-to-surface Euclidean distance, P2S, for assessing the accuracy of the reconstructed hand mesh. The results are compared to several baseline methods, including mono with vertex albedo, LISA, hand avatar, hand NARF, and live hand. The experimental results demonstrate that the proposed XHand approach achieves the best rendering quality, with a PSNR of 34.3 decibels, while maintaining real-time performance at 56 frames per second. The fine-grained mesh is estimated by XHand outperform previous approaches using volumetric representation. The feature embedding modules require 0.7 milliseconds, inverse rendering requires 15 milliseconds, and the neural rendering module needs 0.1 milliseconds. The evaluation of mesh reconstruction quality on the DeepHandMesh dataset shows that XHand achieves the lowest average P2S distance, indicating improved accuracy in reconstructing the hand mesh. The ablation study demonstrates the effectiveness of the proposed approach. However, the study assumes that the hand mesh can be represented as a combination of a coarse mesh and a displacement map, which may be a limitation. Future work may involve exploring alternative representations and improving the robustness of the model to varying lighting conditions and hand poses. The proposed method is evaluated on the DeepHandMesh dataset, with results presented in Table 2. It outperforms the annotated mono mesh and DHM by 3.3 mm and 1.2 mm on point-to-surface, P2S, error, respectively. This indicates that the feature embedding module can accurately capture hand mesh deformation, surpassing the encoder-decoder scheme in DHM. Visual results on image synthesis are shown in Figure 6, where the proposed method is compared to hand NARF, live hand, and mono with albedo. The hands rendered with pure white color highlight the level of mesh detail. The proposed method exhibits more prominent skin wrinkles and finer details, such as folds and textures, compared to the baseline methods. Figure 7 presents additional visual results on the DeepHandMesh dataset, demonstrating the proposed method's ability to produce highly detailed hand models. The method effectively captures intricate features, such as folds and textures, resulting in enhanced rendering quality and geometry quality. The proposed method's superiority is attributed to the feature embedding module and the topological consistent mesh model. The feature embedding module allows for accurate capture of hand mesh deformation, while the topological consistent mesh model enables the preservation of fine-grained hand geometry. In contrast, the baseline methods, such as mono and hand avatar, exhibit limited expressive capability and smoothing effects, respectively. Hand NARF and live hand yield competitive render results but rely on the mono model and cannot obtain fine-grained hand geometry. The results demonstrate the effectiveness of the proposed method in capturing accurate hand representation, outperforming state-of-the-art methods on the DeepHandMesh dataset. The method's ability to produce highly detailed hand models with intricate features makes it a valuable contribution to the field of hand modeling and image synthesis. The XHand method efficiently generates personalized hand expressions from arbitrary hand gesture inputs, leveraging in the wild data as a reference for hand poses. Pose parameters are extracted from Hamer, a robust pose estimation framework. A comprehensive ablation study evaluates the impact of various components on the XHand model's performance, including feature embedding, part-aware Laplace smoothing, and position encoder. The results, presented in Table 3, demonstrate that the feature embedding module significantly enhances rendering quality, with a notable decrease in LPIPS and increases in PSNR and SSIM. The part-aware Laplace smoothing strategy yields more realistic geometric results, indirectly improving neural render accuracy. The position encoder in neural rendering leads to better image quality. An additional ablation study, presented in Table IV, investigates the effect of the number of input views on the XHand model's performance. The results show that the model's performance improves with an increasing number of input images, achieving optimal performance with 30 views. This is reflected in a decrease in LPIPS and increases in PSNR and SSIM. The XHand method outperforms other neural rendering networks in terms of both performance and efficiency. The use of multilayer perceptrons, MLPs, enhances inference speed and rendering quality, ensuring efficient and high-fidelity output. The ablation study highlights the contributions of various modules and settings within the XHand framework, demonstrating the effectiveness of the proposed feature embedding module, part-aware Laplace smoothing strategy, and position encoder. The XHand model exhibits robustness across different numbers of views, achieving good performance even with limited viewpoints. Furthermore, the study suggests that using different spherical harmonic coefficients for relighting can enhance the vividness of the generated images. Overall, the XHand method efficiently generates personalized hand expressions from arbitrary hand gesture inputs, with the ablation study validating the contributions of various modules and settings within the framework. Generating personalized hand expressions from given hand gestures is a challenging task in computer vision and machine learning. To address this, a novel approach is proposed, leveraging the monoparameters extracted from Hamer, 42. This method enables accurate and efficient translation of a wide range of hand poses into detailed, individualized hand representations, ensuring high fidelity and adaptability across various input gestures. The proposed method utilizes a mesh-based neural network to generate realistic hand expressions based on any given hand gesture. Visual results on wild images demonstrate the capability of this approach in producing highly detailed and realistic hand expressions. Ablation experiments were conducted to evaluate the impact of different modules, such as feature embedding, on the final results. The findings suggest that the proposed method yields highly detailed results, particularly in regions marked by red, indicating more realistic outcomes compared to other methods. A key limitation of current hand reconstruction methods is the insufficient training data, leading to reconstruction failure. To address this issue, experiments were conducted using different numbers of views as inputs, demonstrating the effectiveness of the proposed method even with a limited number of viewpoints. In terms of neural rendering, the proposed mesh-based network is compared to traditional neural radiance fields, 20, and other methods like UNet, 62, and EG3D, 61. The results show that the proposed method achieves competitive rendering quality and inference speed compared to these alternatives, highlighting the advantages of using a mesh-based network for neural rendering. The proposed method demonstrates promising results in terms of visual fidelity and adaptability, making it a valuable contribution to the field of computer vision and machine learning. By leveraging the monoparameters and a mesh-based neural network, this approach enables the generation of personalized hand expressions from hand gestures, addressing the limitations of current hand reconstruction methods. XHand is a real-time expressive hand avatar system that achieves photorealistic rendering and fine-grained geometry. The method utilizes effective feature embedding modules to distinguish between average features and pose-dependent features, resulting in finely detailed meshes that accurately capture hand poses. A mesh-based neural render is employed to ensure high-quality hand synthesis, maintaining mesh topological consistency. To reduce artifacts while preserving details, part-aware Laplace regularization is introduced during training. This approach applies different levels of regularization to achieve a balance between detail preservation and artifact reduction. Ablation experiments were conducted to evaluate the performance of various network architectures, revealing that a 4-layer UNet achieves superior rendering quality, albeit at the expense of inference speed. In contrast, multi-layer perceptrons, MLPs, can enhance performance by 20% with only a marginal loss in accuracy, making them the chosen neural renderer. The authors also investigated the suitability of the EG3D image generation network for neural rendering but found it unsuitable for this task. Rigorous evaluations were conducted on the InterHand2.6M and DeepHandMesh datasets, demonstrating the ability to produce high-fidelity geometry and texture for hand animations across a wide range of poses. The method relies on accurate mono annotations provided by the dataset during training. Future work will consider exploring effective mono-model parameter estimators to further improve the system's performance. The XHand system's ability to produce high-quality hand animations is attributed to its effective feature embedding modules and mesh-based neural render. The use of part-aware Laplace regularization and MLPs as the neural renderer enables the system to achieve a balance between detail preservation and artifact reduction. The results demonstrate the potential of XHand for various applications, including computer-generated imagery, virtual reality, and human-computer interaction. The paper introduces a novel method for reconstructing personalized semantic facial nerve models from monocular video. This approach leverages deep learning techniques to create animatable 3D neural models, suitable for applications such as virtual reality, gaming, and film production. The authors first provide an overview of existing methods for creating 3D models from video data, highlighting their limitations and the need for more accurate and personalized models. Their proposed method combines neural networks and traditional computer vision techniques to achieve high-quality results. Key components include a neural network-based face detection system, a semantic segmentation module to identify different parts of the face, and a NeRF model reconstruction algorithm. Techniques used to improve accuracy and efficiency include using multi-view video data and incorporating prior knowledge about human facial structure. Experiments demonstrate the effectiveness of the proposed method, including comparisons with state-of-the-art techniques and evaluations on different types of video data. Results show that the proposed method can produce highly detailed and personalized 3D models that capture subtle variations in facial expression and appearance. In conclusion, the paper presents a significant advancement in the field of 3D model reconstruction from video data, offering a powerful tool for creating realistic and personalized avatars for various applications. The proposed method has the potential to revolutionize the way we interact with digital content and could have far-reaching implications for industries such as entertainment, advertising, and healthcare.